So in this lesson, we're going to look at this idea of energy, and we're going to expand on the topic and look at it in detail. So the learning outcome for this lesson, so students should be able to explain energy conservation and analyze processes in terms of energy changes and dissipation. So that's what we're going to look at. We're going to, by the end of this, hopefully have an idea of this learning outcome. So what does energy mean in science? So energy is the ability to do work. So that is essentially what energy is. So it's the ability to do work. So the units of energy, so the unit we use to measure energy is the joule. Okay, and it has a capital J. That's what we use to measure the unit. And the same unit as used for work. So work involves moving an object. Since energy is the ability to do work, then energy is the ability to make things move. And if we have a look at this example, we have students here playing basketball. So there's a lot of movement going on. So they have to physically move their bodies, they have to move the ball around the court, and that all takes energy. So energy is the ability to do work. And just to kind of go back and link this in, so we talked about this idea of work. So if we remember the concept of what's called a force. So if you remember, a force causes an object to move, so either it can cause an object to move, speed up, slow down, change direction, or it can cause an object to stop. So that's what's called a force. And if we remember, we measure force using a Newton. And then if we think about work, so work is basically force multiplied by distance. Okay, and the unit that we use for work is this thing what's called the Newton meter. Okay, so you have the force part acting on the object, and then you have the distance that it moves. So if we take this, so imagine this is an object here, and we apply a force. Okay, so let's say apply a force of, let's say 10 newtons, and we move this object, let's say it moves from here over to here, so we move at a distance of, let me just change that actually. We apply a force of 1 Newton and we move it, let's say, a distance of 1 meter. So a force of 1 Newton and we make it move a distance of 1 meter. So this would be, the work done would be 1 Newton meter. And this Newton meter, 1 Newton meter, is what is equal to 1 joule. So you can think about like 1 joule is the energy. 1 joule is a measurement of energy, but basically it's a force of 1 Newton acting to move an object, let's say 1 meter. So that's the link, if you like, between this idea of force and work and this idea of what's called a joule. So going back to our definition, so energy is the ability to do work, and work is basically applying a force to move an object a particular distance, or it could also be like applying a force to make something slow down, change direction, etc., etc. So if we think about this in relation to the guys playing basketball, so these guys are moving, they're moving around constant distances, they're applying force, for example, to move the ball around the court. They're moving different distances around the court, so therefore work has been done, so therefore energy is needed to do that work. So joules of energy are being used in the playing of the basketball. And then just as we say, so the unit is the joule, and work involves moving an object. Since energy is the ability to do work, then the energy is the ability to make things move. Okay, so that's the kind of way to kind of think in your head about this concept of energy. So energy is the ability to do work or make things move. Now the interesting thing as well is that we have, if we take the world, so if you look like if we take the world, we have two things essentially that make up everything in the world. So you have matter. So let me just, okay, so you have matter. Okay, and if you think about matter is essentially made up of atoms, and it has two properties. It has mass, and it takes up space, so it has volume. So if you look, for example, at any object in the room, if you look at a chair, for example, in the room, that chair is made up of trillions of atoms, and it has mass. So if you were to put it on a scale, it would give you a mass, and it also takes up a definite amount of space. And then the other thing then, so you can think about matter as like the building blocks. And then you have this thing called energy. So energy is basically what gives life, if you like, to everything that's around you in the room. So if you take the chair, for example, the atoms that make up the chair are being held in place by energy. And it might look like a static object that's just sitting there, but there's an awful lot of energy that's in that chair as well. So basically energy then is the second thing. So everything is made up of matter, and then you have energy that basically causes the matter to do work, or causes the matter to move or change direction or move around. So you can kind of think about it like that. The room that you're in, for example, is full of air. You can't see the air, but that air is actually being moved around. It's not just staying in place. The particular particles of oxygen and nitrogen and carbon dioxide that's in the air, they're being moved around, and it's the energy. So, for example, energy is moving around. And there's this really interesting concept then as well. So matter, so there's conservation of matter and conservation of energy. So matter can't be created or destroyed. It's just changed from one form into another. So matter is constantly being changed around. So the atoms that make up your body have been around as long as the creation of the earth, for example, and the energy that's in the earth has also been around as long. It's just constantly been changed from one form into another. So that's what we're going to look at now. We're going to look at the different forms of energy. So energy, as I say, energy can't be created or destroyed. It's just constantly changing from one form into another. So if we think about then, what are the different forms of energy? So there are many different forms of energy, and these include, so we have kinetic energy. So kinetic energy is the energy that a body has because it's moving. For example, a ball rolling along the ground or a surfer on a wave. So we have this stuff called kinetic energy. And a way to kind of think about that is so imagine so this is the ground, and you roll a ball. So the ball will move. Okay, so once it's moving, it has this thing called kinetic energy. So when an object is moving, it has kinetic energy. For example, when a car is moving, it has kinetic energy. Anything that moves that has mass has this type of energy called kinetic energy. So a ball running on the ground or a surfer on a wave. Okay, so that's the first kind of form, kinetic energy. So you can think about it as the energy an object has because it's moving. So again, like this, if you take a surfer, for example, they're moving along on a wave, and they have this, what's called kinetic energy, or energy because of movement. Then we have this other substance called potential energy. So potential energy is the energy that a body has because of its position relative to other bodies. For example, a stationary object raised above ground level. Changing the shape of an object can also involve potential energy, for example, a spring. So potential energy then, if we think about the same kind of example of a ball, so imagine we have a hill like this. And imagine the ball is just sitting on the top of the hill, so it hasn't moved or it hasn't changed direction. But what this object, because of its position relative to the ground, it has a lot of potential energy. So we know that if we just slightly nudge that ball, it's going to fall down the hill. Okay, and it will fall down the hill with a particular amount of force, for example, and it has a lot of potential energy. The same way as well, if you take, for example, if an object, imagine you have a spring, for example. So imagine the spring is like this, okay, so it's not compressed. And then if you compress that spring down into a tiny little space like this, okay, so you've gone from distance from here to here down to this tiny distance here. So you compress it like that, and you know that if you let this go, it's going to fly. So what happens is so this here has a lot of potential energy. When it's compressed like that, it has a lot of potential energy. And then the minute you uncompress it or let it go, that potential energy changes form and it changes into kinetic energy and it moves. Okay, so you have this. This is another example of potential energy. So this is the part here when it talks about changing the shape of an object also involves potential energy. And the same even as well with a balloon. So if you take a balloon, for example, so you have a balloon like this, okay, and it's not inflated, and then if you blow it up, so imagine you blow it up like this and you hold the end of the balloon. Now it has high potential energy. So it has a lot of potential energy. So imagine the potential energy here is high. The potential energy when it's in this state is pretty low. So now it's high potential energy. And if you let this balloon go, the kinetic energy will change then into kinetic energy. So it changes form. So energy is not created or destroyed, it's just changed from one form into another. So you get this change into kinetic energy. So potential energy then is the other form of energy. So you have kinetic energy is the energy an object has because it's moving. Potential energy is the energy an object has because of its position. So for example, its position relative to other things. So like a ball or a car on top of a hill has a lot of potential energy. Or because of its shape, for example, or a change in its shape, like a spring or like a balloon, for example. The next kind of form then is what's called sound energy. So sound energy that is produced by vibration. For example, the sound produced by a guitar string vibrating after it's plucked. So again, that's another form of energy. So if you imagine the string, it's like this. Okay, so there's no work or whatever being done, but the minute that string is plucked, what will happen is the spring will start to vibrate. So imagine it start to vibrate. So what you get then is, and so this vibration then, what it'll do is it'll vibrate the molecules all around in the air. So imagine in the air then, so sound needs a medium to travel through, so it'll vibrate the molecules in the air, and then what you'll get is you'll get this sound wave that moves out from the source, for example the string. So you get this sound wave that's moving out through space, and then what that'll do is it'll hit a person's ear, and then that sound will change into a different form of energy in the ear, so it'll vibrate the eardrum, and that will send an electrical signal to the brain, and then the brain will perceive that then as a sound, and it will change. So the energy is changing from one form into another. So again, that is sound energy. So energy is produced by vibration. For example, the sound produced by a guitar string after it's been plucked. Okay, so you have kinetic energy, energy of an object because it's moving. You have potential energy, which is the spring, for example, and the balloon and the object on top of a hill. And then we have sound energy, which is just vibrational energy that moves through the air as sound waves. The next form then is heat energy. So energy that travels between a hot object and a cold object. For example, when a spoon is placed in hot tea, heat travels from the tea to your fingers along the spoon, or also as well in a thermometer as well. So if we think about this heat energy, so if we remember back to, we talked about what heat is. So basically heat is just the vibrate, so everything is made up of atoms. So if we take a spoon, for example, a spoon is made up of atoms, and those atoms are all, let's say, like in proximity to each other. So they're all kind of close to each other like this. So imagine this is like a section inside the tea. So temperature then, if we apply energy to one of these molecules, what's going to happen is it's going to start to vibrate. and then that will cause the one next to it to vibrate, and it'll cause the one next to it to vibrate, and so on and so forth. And this vibration then is what we perceive as heat. So if you were to put your hand then, let's say when all of these are vibrating, and you were to put your hand to that hot object, that will cause the atoms in your fingers to vibrate, and we perceive that as hot, okay, as heat. So heat energy, so heat again is a form of energy. So heat has the ability to make atoms do work or cause them to move. So, and the way that heat moves is, so imagine we have an object, so imagine this is like, so you have, imagine this end of it is hot, or we heat up this end here. So whatever we, let's say, apply a candle flame, so we're applying heat. So imagine this is like a piece of metal. So what's going to happen is this part is going to get hot. And then imagine this side here is cold. So what will happen is the heat, so if we think about the atoms here, so the atoms in this section of the bar are going to be vibrating because they're hot. So what they're going to do is they're going to cause the atoms next to it to vibrate. Okay, so these will start to vibrate, and then the atoms next to them will vibrate, and then the atoms next to them will vibrate. And what you will get is you'll get this movement of heat through the bar. So essentially the way that heat moves, it moves from hot to cold. So heat energy goes from hot to cold, or hot or cooler. So that's the way heat moves. It doesn't move in this direction. It doesn't go from cold to hot. It moves from hot to cold. So that's the way that heat energy moves. And that's how a thermometer works. So essentially what a thermometer does, when you, for example, put this into your mouth or whatever, the heat energy that's in your mouth, it causes the atoms at the end of the liquid here to start to move and expand. And what happens is the heat energy moves through the liquid, and it causes the liquid to expand, and it rises up the thermometer, and it rises up in a predictable way that we can determine then, well, how much energy was at the source in order to make the liquid rise up the thermometer. But that is what's known as heat energy. So heat is another form of energy, and it moves from hot to cold. Then we have what's called chemical energy. So chemical energy is that energy that's stored in food and batteries, and are good. So food and batteries are good examples of chemical energy. So again, in food, we have energy that's stored as chemical energy. It's stored in the chemistry, if you like, of the food, and again, it's the body can take the energy out of that food and use it to do work. And then likewise as well, inside batteries, you have chemical energy that's stored as well. And if you attach this up to a circuit, it causes the circuit to do work, and that energy is changed from one form into another. So a really good example in relation to this chemical energy, if we think about respiration. So respiration. So respiration is, so we have C6H12O6 plus O2, which is oxygen, and our body burns that, and it produces CO2 plus H2O plus energy. So if we think about what these are, so we have, this is glucose, okay, so we get glucose from plants, and inside glucose, inside the bonds that make up, like that attach these atoms together, you have energy that's stored in here. And then what happens is the body, we breathe in oxygen, and then that's combined with glucose. And through this process of respiration, this is how the body makes the energy that it needs in order to carry out all the functions that the body needs to carry out. And then when your body burns glucose using oxygen, what happens is it produces carbon dioxide, it produces water vapor, so we breathe these out, and then it also releases energy. And that's when we talk about chemical energy, that's what we mean. It's the energy that's stored inside the chemistry, for example, of molecules like glucose. And this energy then is used to heat the body. And then it's used for everything. It's used for you to do work like talk and move around and things like that. Your body needs energy, and it gets it from glucose and breathing in oxygen, and combine these two together in a process that's called respiration that happens inside the cells. So if this process wasn't happening, your body would not be able to make energy, and therefore you would not be able to live, basically. So chemical energy, that's what we mean by that's one example of chemical energy. So in food you have glucose, and that glucose, when you eat food, is extracted and burned in the body to produce energy. And then you have chemical energy then that's in batteries as well. So that is chemical energy. So the next form of energy then is what's called electrical energy, and we're very familiar with that. We've looked at lots of components and the flow of electricity. So energy that comes from the flow of electric charge. For example, electric current flowing along a copper wire. An electric car uses electrical energy to make it run. So again, this is another form of energy that you have. You have electrical energy, and if we remember, so electrical energy, if we have, so imagine this is a piece of copper, and imagine that inside the copper then you have, so the copper is made up of atoms like so, and then you have electrons. So imagine this is our electron here, so these are electrons. So what's going to happen is, so we'll just label this, so this is copper, and then this is electrons. So the electrons, so what's going to happen is you will have this force that comes, so a positive force that comes from the battery, and this is like the voltage of the battery. And what will happen is the electrons will be pulled through the copper wire, and as they move through the copper wire, they will hit against, for example, the atoms that are in the copper wire, and those atoms will move. They'll cause them to vibrate. So this flow of electricity can be used to do useful work. So for example, when it flows through a piece of copper, it can cause the copper to vibrate, and it can start to give off heat. So what you have is you have electrical energy. So electrical energy is just the energy from the movement of these electrons. So what you can do is you can put things in front of the electrons and get them to do useful work. Like, for example, if we have a heating element, so imagine you have, like, you get the electrons to move through a piece of wire that's really, the atoms are really packed closely together. So what's going to happen is it's going to be hard for the electrons to move through this copper wire. So as a result of that, the copper wire will move through it, but the copper wire will get really hot and it'll give off heat. And this can be used as, this could be like a bar, for example, that's in an electric heater. So basically what you're doing is you're getting the bars that are in the heater really hot because of the movement of electrons through it, and then it'll radiate out heat, and that can be used then to heat the room. But again, that's using electrical energy to do work. And the same principle then in, if you were to take a light bulb, for example. So in a light bulb you have a coil of a material called tungsten, and again, if you have this movement of electrons through this tungsten, what will happen is the electrons, it's difficult for the electrons to move through it, so they're forced through it, so they cause the atoms in the tungsten to vibrate really rapidly, and they cause them to vibrate so much that they go white hot. And when they get white hot, they give off light, and that light then is used to illuminate the room. And again, these are examples of how the conservation of energy as well. So energy is just being changed from one form into another. So it's been changed here from electrical energy into heat energy, or it's been changed from electrical energy into light energy. So again, this is electrical energy, and basically electrical energy is just the flow of electrons, the flow of electricity. So you use that to do some useful work. The next form then is solar energy, and this is really, really important, solar energy. So if we take, for example, the sun, so imagine we have the sun, so this is the sun. So this is our sun. And the sun is roughly, it's about 98 million miles away. So let's say this is the Earth here. So this is the Earth. So what happens is that energy from the sun, it travels through space and it reaches the Earth. Okay, and it reaches, so this energy is what's called solar energy. So it's solar energy. And this solar energy is really important. So this ultimately is where all of the energy that's on the Earth, where it comes from. So this solar energy. And plants have this amazing capacity, so through photosynthesis. So basically plants can harvest the energy from the sun, and then we get our energy from the plants. So if we take, for example, the process of photosynthesis, it's just respiration in reverse. So if we take, so what does a plant need? So it needs, so CO2, which is carbon dioxide. It needs water, which is H2O. Okay, and then it uses light. So light from the sun, so it takes this solar energy, and it also has this green stuff called chlorophyll. Okay, and that's inside the leaves. And what it does is it combines these together and it uses it to make its own food. So it traps this energy from the sun in glucose molecules. So it traps it in, so glucose, and then it also gives off oxygen, O2. Okay, so this is the process of photosynthesis, and what happens then is humans come along and we eat plants, and animals eat plants, and they take the energy that's trapped inside here and they use through respiration, they use that to, produce energy like what we've just talked about. So basically what the plants have the ability to do is they can take this solar energy that travels from the sun and they can trap it as chemical energy inside glucose molecules inside the plant. And then we can come along and eat the glucose molecules and get energy from our food, for example. So we get that chemical energy. So solar energy is another form of energy, and it comes from the sun. And we can use solar panels to take this solar energy and turn it into electrical energy and use that electrical energy then to do some useful work. But we're not as efficient as plants are. So plants basically use chlorophyll. It's the substance it's the green substance it's a chemical that makes plants green, but it has the ability to trap the energy from the sun and turn it into and store it in glucose molecules. So that is solar energy. So solar energy is energy that comes from the sun. And then we have this other form of energy, which is known as nuclear energy. So nuclear energy, nuclear energy is used in nuclear power plants. So energy produced from nuclear reactions, for example, nuclear fusion or nuclear fission or nuclear fusion. So we have these two processes of where energy comes from the nucleus of atoms. So if we remember the atom, so imagine you have hydrogen, for example, it's the first element on the periodic table. So hydrogen essentially has, imagine like it has one proton, let's say one neutron, and some forms don't have any neutrons, and then it has around it, then it has one electron. So you have the electron, you have the proton, and then let's say in some forms you have the neutron. So inside, so this here is the nucleus of the atom. So this is the nucleus. And this is where nuclear comes from. So nuclear energy has got to do with the nucleus of atoms. So if we take the sun, for example, and so the process, like how does the sun make its energy? Well, it makes its energy, what it does is it takes, so imagine this is just, this whole thing here is just one hydrogen atom, and then this is another hydrogen atom. So this is hydrogen, and this is hydrogen. And what the sun does essentially is it forces these two together, and they combine. Okay, so they combine together. It forces the nucleus of hydrogen together, and that turns into helium. Okay, so it goes from from two hydrogen atoms. They're forced together, and it produces helium. And this here is like a nuclear explosion. So it is, and it happens in space. And that nuclear explosion, what it does is it gives off huge amounts of energy. And that energy can be used then to do work. So that's like the way that the sun makes its energy. So it fuses two atoms together, and when it fuses them together, it releases huge amounts of energy in the form of like solar energy. So that's released. So this, you can think about the sun. When you look at the sun, it's basically a controlled nuclear explosion that's happening in space. Now, we have another process, basically, which is called fission. So we use uranium, and you can think about uranium as this really big atom. So it's a big atom. So it's a big atom like this. And what happens is we basically fire like a neutron at the uranium. And what that does is it causes it to break or split up. So it causes it to break down, or fission. So it breaks down. And when it breaks down like this is like a controlled nuclear explosion. And what will happen is that will give off heat. And basically that heat energy then can be used to heat water, make steam, and then that steam can be used to turn a turbine, and that turning of a turbine then can make energy as well. But nuclear energy it comes from these two forms. So you have fusion that the sun uses to combine the two atoms of hydrogen together to make helium, releasing solar energy. And then you have fission, which breaks down like bigger elements like uranium, and it releases energy as well. And that's the basis of how nuclear power plants work. So that is what's called nuclear energy, and again, that's another form of energy. Now, I've talked about the principle of conservation of energy. So let's kind of look at this in a little bit of detail. So the amazing thing about energy is that it never goes away. So energy does not get used up. Energy changes from one form into another. So energy doesn't just disappear, it changes from one form into another. So the chemical energy stored in a battery can change to sound energy you hear from your mobile phone. So for example, the battery that's in your mobile phone, it stores chemical energy. And then if you play a song on your phone, for example, that chemical energy is turned into sound energy. The chemical energy in food that we eat can change to kinetic energy when we move. So if we remember this example up here, so this one here, so for example, so this is respiration, this is how we make our energy. So we eat glucose, and we breathe in oxygen, and then through the process of respiration, we make energy. So then that energy, then we can use it, for example, it can be changed into kinetic energy when we walk around. Where do we get the energy to walk around? It comes from our food. Specifically, where does it come? It comes from the energy that's in glucose. Where does this glucose come from, and where does the energy in the glucose comes from? Well, it comes from this process of photosynthesis. So photosynthesis gets the energy into the glucose through this process here. Plants are able to take energy from the sun, trap it in these molecules, make glucose that has the trapped energy, and then we can eat the glucose to get our energy. So again, that's energy is constantly being changed around. Then nuclear energy can change to electrical energy. This electrical energy can change to sound energy, heat energy, and kinetic energy. So again, if we take, for example, this nuclear energy, this is the basis of how power plants produce electrical energy. And then that electrical energy then can be used in the home, for example, to make sound if we listen to the radio, or it could be used to heat our home if we use, for example, electric heaters in our home. So the fact that energy never gets used up leads to a famous principle in physics, and this principle is called the principle of conservation of energy. So energy is neither created nor destroyed, it is just converted from one form into another. So that's what we mean by the conservation of energy. So energy is not created or destroyed, it's just changed from one form into another. So that's kind of like what happens. Energy is constantly being changed from one form into another. So what can happen then is that like systems are not 100% efficient, so energy can be wasted. So wasted energy is a challenge to us all. We must reduce the energy we waste. While it is true that energy never gets used up, energy changes from useful forms to not so useful forms. So there is a very great need to avoid wasting useful forms of energy. And this is what we mean when we talk about energy conservation. So it basically means that we have systems that can take the energy that's produced and use as much of it as possible. So what is the meaning of energy dissipation? So this idea of energy dissipation. So energy dissipation is when energy changes from a useful form to a not so useful form. So for example, the food we eat provides the chemical energy we need to walk. When walking, our bodies produce heat energy, and some of that heat energy passes into the air around us, so we have no way of making use of this. Some of the original chemical energy has been dissipated. So if we go back up here to respiration, so our body burns glucose in order to make energy. So basically what happens is, let's say we walk around. This is us, and we're walking along. Let's say what we're doing is we're taking this chemical energy that's stored in the glucose. So the chemical energy that's stored in the glucose. So every time you walk, your body is burning glucose, using oxygen and burning glucose, and it's making the energy that you need in order to be able to walk. But what happens is, as you know, when you start to walk, you start to get hot. And that heat energy that comes from the muscles in your body, that heat energy is dissipated into the environment around you. So you lose heat to the environment. But that heat energy that you're losing, it's not doing any useful work. Okay, so it's just lost to the environment. So that's what we mean by when we talk about energy dissipation, that's what we mean. So the energy from the glucose in your body that's been used that's turned into kinetic energy that makes you move is been used to do some useful work. But the energy that you lose, for example, to the environment is just lost in the environment, and it's not doing any useful work. So in a very simple way, you could refer to energy dissipation as a waste of useful energy. Okay, so you can think about this heat that's been lost from your body. It's a waste of energy essentially, because it's not doing any useful work. So let's look at some examples of energy. So we've kind of talked about some examples of energy change as I went through the different types of energy that we look at. But let's think about some specific examples of energy change. So remember, energy can't be created or destroyed. It's just changed from one form into another. So we look at some examples of energy changes and consider how much energy is dissipated. So if we think about the example of solar water heaters, so the energy from the sun, so if we take here, we'll go back down here to our energy from the sun. So again, think about the energy that's from the sun. So the sun is producing loads of energy through this process of nuclear fusion. That energy is traveling across space and it's traveling to the Earth. So the energy from the sun is referred to as solar energy. So solar energy can be used to heat water in specially designed glass pipes. So this hot water is stored in a tank and can be used for baths, showers, washing clothes, etc. So you will use less electricity or natural gas to heat your water. Okay, so this is an example of, so you have, for example, this solar panel. You have this solar energy that's coming from the sun, and what that does is it heats, so the water flows through this panel and it gets heated up. So the heat from the sun is exchanged into the water, and that heats the water. And then we can use that water then to, for example, heat a radiator, and then that energy will heat the room, and then that will be used to keep the room warm. So instead of us, for example, turning on the immersion, we can use solar energy to take the energy from the sun, take solar energy and convert it into heat energy in the water. So you're getting this change of energy. So it's changing from one form into another. So you're getting the energy change that occurs is from solar energy to heat energy, and a large amount of solar energy is dissipated. However, with improvements in design, more and more of the solar energy is changed to useful heat energy. So again, our systems can't trap all the energy from the sun, it can just use a fraction of it. And a lot of the other energy from the sun is just wasted, so it is. Or not wasted, but dissipated. It's not being put to do useful work like heating up the water. Another example of energy change is the bicycle dynamo. So a dynamo is a device for converting mechanical energy or movement energy into electrical energy. So dynamos are often found built into the front wheel of a bicycle to power a light, and here's a look at how we may convert energy. So this is a dynamo here, and basically as you cycle, the tire moves around, and it causes this piece here to move around as well. And what that does is it takes this mechanical energy from the wheel of the bike moving around, and through the process inside the dynamo, it changes that energy into electrical energy, and that electrical energy goes up and it goes through the bulb, and it causes the bulb to get really hot and it changes the electrical energy into light energy. So you get out of bed early on a day that you plan to cycle to school, and it might be a bit dark, so you use one of these guys. You eat a good breakfast, or we could say you consume a lot of chemical energy, so you get the glucose, for example, that's in cereal. Some of this chemical energy will be changed to kinetic energy as you cycle. So when you're cycling your bike, you're burning up energy. That energy has been used to move the bike forward. A certain amount of chemical energy will be dissipated into the air as heat energy from your body. So for example, you're losing heat as you're cycling to school. And as the bicycle is moving, some of the kinetic energy will be changed to electrical energy by the dynamo, and a certain amount of kinetic energy will be dissipated as you try to cycle against, if there's a breeze, for example. And some of the electrical energy will be converted into light energy in the bulb connected to the dynamo, and a certain amount of electrical energy will be dissipated as heat energy into the air as the bulb heats up. So this is kind of like the process. So this is the piece that's attached to the wheel. So you have the bicycle dynamo. So it rotates this magnet, and you have coils of copper wire inside here, and you have like a permanent magnet, and this movement of a permanent magnet inside the dynamo around copper produces electrical energy. So it gets electrons moving through the system. So that's an example of the conservation of energy. So energy is being constantly changed from one form into another. So the last thing we want to look at then is this idea of how to represent energy changes in a system, and we have these what are called Sankey diagrams. So Sankey diagrams are named after H.R. Sankey, a Tipperary-born engineer, and he used them in 1898 to describe energy efficiency of a steam engine. So you have a steam engine here. So inside here you have coal that's burned to produce heat, and that heat is used to heat water and make steam, and then that steam that comes from the water is used then to turn a piston, and then that piston, for example, is used to make the train move forward, for example. So again, you have this conservation of energy being changed from one form into another, into another. But these Sankey diagrams are useful ways to think about and look at this change of energy. So Sankey diagrams show the flow of energy to and from a device. And in a Sankey diagram, the width of each arrow represents the proportion of energy named. And below are 3 Sankey diagrams to compare the energy flow to and from 3 different types of light source. So if we have a look at this, so you have this guy, so this is a filament light bulb. So imagine so this is the setup here, so you have electrical energy that's moving through the light bulb. That's moving through like a piece of copper, and then it'll go through the light bulb itself. So you have electrical energy, and then that's being converted into light energy, okay, through this process that we've talked about. So in this is a way to represent it. So you have, for example, this part here represents the energy that's going in. So imagine you have the energy. So if we take this here, so if we take this here, and we just move this over here so we can kind of get an idea of what's happening. So what we have here is, you can think about, imagine in this case that's represented in the diagram. So you have 40 joules, okay, so you have 40 joules of electrical energy that's going in, okay. Then you have, so only 0.8 joules is being converted into light energy. 0.8 joules is being turned into light, and that's the purpose of a light bulb. It's to take electrical energy and turn it into light energy. So out of the 40 joules, only 0.8 joules is being turned into light. And where's the rest of it going? Well, the rest of it is being lost as heat. So for example, the bulb gets hot, and let's just do this in a different color. So imagine then you have heat. So you've heat that's been radiated off a bulb. And if you have these old filament bulbs, like, I don't say put your hand on it, but if you put your hand near it, you'll actually feel the heat that's coming off the bulb. So don't obviously touch the bulb, that's very dangerous and you'll burn your hand, but you can actually feel the heat that's been coming off the bulb. And what's happening is, so the bulb is supposed to produce light energy, but it's only producing a small fraction of light energy, 0.8 joules. It's taken up for 40 joules, and you have like 39.2. So 39.2 joules is actually being lost as heat. That's what's being lost as heat. So this can be represented in one of these what are known as Sankey diagrams. So this here is the input, so it's the input that's going in. Then you have this here, like this thickness of the arrow represents the amount that's been changed from electrical energy into light energy. So you have that, and then this here is showing the amount of energy that's been lost or wasted, that's been turned into heat energy. So the bulb gets hot, and that heat is dissipated into the environment. And this is an example of the conservation of energy as well. So energy has been changed from one form into another. So if we have a look at then just some other examples. So this one here, so this is an LED, light emitting diode. So it takes in 4 joules, so it takes in much less energy than a filament lamp. And again, it takes, out of that 4 joules, it takes 0.8 joules is turned into light energy, and then 3.2 joules is lost as being lost as heat energy. And then if we take this, so Cfl lamp, okay, so it takes in 9 joules of electrical energy, and so 0.8 joules is being turned into light energy, and then the rest of it is being lost as heat energy. So as well. So these are Sankey diagrams, and these are the ways that you can look at them and use them. So then if we think about some simple calculations in relation to this, so if we want to look at, let's say, the efficiency of a bulb, so we can use this diagram to represent that. So by using the information in the diagram, compare the electrical energy that is put into the filament lamp with the amount of energy produced, and calculate the percentage of light energy produced in each case. Okay, so that's what we kind of like want to look at. So if we think about how do we do this, so if we think about the filament lamp, so with the filament lamp we have, for example, 40 joules of energy going in, 0.8 joules of that has been turned into light energy, and then 39.2 joules has been lost as heat energy. So what we can do is we can calculate the percentage. So we do the amount of light that's being produced is 0.8 divided by 40 multiplied by 100 over 1. So we can see that it has a 2% efficiency. So what that means is that of the amount of energy it takes in, only 2% of that is being turned into electrical energy. So okay, so if we think about, so the efficiency, so it's turning 2% of the electrical energy into light energy. So that's the filament lamp. And if we look at the same for the LED, we do the calculation, so we can see that it's a little bit more efficient in that it's able to turn 20% of the energy that it takes in into light energy. So again, you're using the same calculations. And then the last one then is this guy here. So you can see that this is taken 0.9. It's able to convert 0.9% of the energy it takes in into light energy. So that is the Sankey diagrams and how to use Sankey diagrams. So we've looked at a lot in this lesson. So if we go back to our learning outcome, just to kind of think about it. So if we think about our learning outcomes, so students should be able to explain energy, conservation, and analyze processes in terms of energy change and dissipation. So we've looked at energy. So if we think about energy, it's measured in joules. Okay, so it's measured in joules. We have the forms of energy. Okay, so if we think about the different forms, we have kinetic energy, we have potential energy, we have heat energy, we have sound energy, we have chemical energy, we have electrical energy, and we have nuclear energy. And we also have, and I'll just put this down here, solar energy. So these are all the different forms of energy. And then we talked about this idea of conservation of energy. So energy is not created or destroyed, it's just changed from one form into another. So for example, we can take, for example, we looked at chemical energy in food being turned into kinetic energy and heat energy. We looked at, for example, how mechanical energy from the movement of the wheel on a bike can be turned into electrical energy through a dynamo, and then that can be turned into light energy, for example, when it runs through a filament in a light bulb. So conservation of energy is just how energy is changed from one form into another. And then we looked at our Sankey diagrams, which show, so you have the input, and then you have, for example, the output. So like some of the energy is being, depending on how big the arrow is, some of the energy is being turned into other forms of energy then as well. So that is kind of just a quick overview of what we have done, and it links in then to this learning outcome. Okay, thank you for listening.